In this video, I will explain the difference between pointwise and uniform convergence, which will turn out to be the key concepts that we need in order to understand why post-selection inference for methods like lasso is failing. So we take a function f of x defined on some domain, so x is within a certain range, and take functions fn of x, which we want to evaluate how they converge to f of x. So n goes from 1 up to infinity, and we're looking at convergence of fn of x when n goes to infinity. And the first definition is pointwise convergence, which says fn converges to f on the domain D if for any fixed point x in D, the difference in absolute value between fn of x and fx converges to 0 when n goes to infinity. So this is the standard way we would tend to look at convergence of functions. Now the second thing is stronger, and that says uniform convergence occurs when the difference between fn of x and f of x, but not for any fixed point, but the supremum over all possible x's in the domain. So we search for this difference and then find the value of x which this difference is largest, and that converges to 0. Then we have uniform convergence. So it seems very close to each other, so let's have another look at what actually makes things different. Now for pointwise convergence, we could rewrite that as saying, well, the difference converging to 0 for all x's is the same as, well, first you take the limit for n to infinity for a fixed x, and then as a next step, you take the supremum over all the x's of that limit. Remember, the supremum is nothing more than the lowest value, the lowest upper bound, so the lowest value that is going to be large equal than this difference everywhere. So you can compare, it's essentially the maximum, although the maximum we cannot always attain. Now, what does uniform convergence say? Well, it says first take your supremum, and then afterwards you look whether this converges to 0. So first we take the supremum of fn minus f, and then we take the limit of n going to infinity. So what we have done is we have swapped the order in which we take supremum and limits. Now this very subtle difference can turn out to really have big implications. So first of all, why do we even care about this stuff when we do statistics? Well, what we implicitly are doing is deriving pointwise results. So what we are doing is we say, well, take a certain data generating process. Let's give values to these parameters. And we look at fixed values. And then we derive the limit distribution. And then what we say afterwards is, well, now this holds for every value of the parameter. So we are really doing what we do here for functions. We take a limit, and then we take implicitly a supremum. In fact, we say for all possible values of the parameter. So we're not doing this uniformity. And as we will see, this can have major implications. In particular, these pointwise limits can give very misleading results about approximations for what happens to finite n. And in fact, if you want to draw reliable conclusions, I will argue that we will need uniform convergence. Now, our functions are distributions. So what we are doing is showing that distributions converge pointwise to a limit. But we are not looking at uniformly over the parameter space of beta. And as we'll see, that is exactly what the oracle property is. It's a pointwise result. And we'll see that because it does not hold uniformly, this is an explanation of why we get these results which are contradicting each other. Now let's first look at some functions to get a bit of a feeling for this before we move on to the actual statistics. So let's take some simple functions and look at whether they converge just pointwise or also uniformly, and what that implies for the finite n approximations. So first take a simple function, which is just x plus x over n, or x times 1 over 1 plus n. Well, pointwise convergence happens to the function f of x is just equal to x. Intuitively, we would just say, well, x divided by n, that will converge to 0, right? Because x is restricted to be between 0 and 1. Well, let's derive that formally using the definition of pointwise convergence. So we take the limit of the absolute value of fn of x minus f of x. Well, that limit is just x plus x over n minus x. So it's just x over n. And we know that x is positive, so we can leave out the absolute value signs. So we have the limit for n going to infinity of x divided by n. But x is just some number between 0 and 1. So this will of course converge to 0. Well, that proves pointwise convergence. Well, we can also do the same for uniform convergence. So now we again look at this difference, fn of x minus f of x. But now before we take the limit, we have to look at the supremum for all x's between 0 and 1. Well, again, this difference is just x over n. And now the supremum means for which axis is this going to be largest? We find the largest upper bound to this number. Well, that's clearly going to be when we plug in x equal to 1. So this supremum is actually equal to 1 over n. Well, now the limit for n going to infinity of 1 over n is just 0. So, well, that's all good. So clearly in this case, uniform convergence holds. And as I will argue, in this case, indeed, f of x is a good approximation to fn of x. Of course, the approximation gets better when n increases, but we don't observe any weird stuff. So we can just have a look at a small picture of this. So here we have the function f of x always in red, and the function fn of x in blue for different values of n. Well, if you take n large, say 100, they are pretty much the same. There is some difference, of course, between fn of x and f of x when n is small, but the way that this evolves for increasing n is a very regular way. So the approximation just gets better everywhere. And this is the uniformity which does that for us. Now let's take a look at another function, x to the power n. And again, x between 0 and 1. First note that pointwise convergence is a bit strange because it depends on whether x is equal to 1 or not. If you take an x smaller than 1, then we know that if we take it to a very high power, the power is increasing to infinity, this will go to 0. On the other hand, 1 to the power n will remain 1. So for any x smaller than 1, so in the half open interval, including 0 but not including 1, the limit is 0. But if x is 1, the limit is 1. So we have a strange jump going from when we approach 1 to actually reach 1. Well, pointwise convergence, again, establishing it formally is straightforward. The difference between the functions is, well, for any x between 0 and 1 is just xn, x to the power n minus 0 is just xn. Well, take this to the power n and n to infinity and you get 0. And here it's 1 minus 1. So, well, that concludes pointwise convergence. But here we have a case, and this has to do, of course, with this strange jump that you have, where uniform convergence does not hold. So let's write it out. We need to take the supremum of the difference. So first take the difference of the functions gn of x and g of x, which is x to the power n, and here I write it as a single function, just 1 if x is 1 and 0 otherwise. Well, where does this supremum take place? When is this value as large as possible? Well, it's not going to be when x is equal to 1, because when x is equal to 1, I have 1 here, I have 1 here. 1 minus 1 is 0. And since the absolute values are rounded, 0 is going to be the smallest value I can actually get. So I can rule out x equal to 1. So that's what I do here. I say, okay, let's rule out x equal to 1 and only consider the half-open interval between 0 and 1. Well, note that my function g of x is actually equal to 0 there, so this part just drops out. So I end up with just the supremum for x between 0 and 1, but 1 not including, of x to the power n. And here comes the tricky part. So before we could take the limit directly without taking the supremum, but now we first have to maximize this number. So we need to make this number as large as possible. Now first note that if I make x larger, then x to the power n will also become larger. So I should move towards 1. And I should move closer and closer and closer to 1. Now I can keep moving closer and closer and closer to 1, and this number x will become also closer and closer to 1. So the largest I can actually get it is the lowest upper bound I can put on it is 1. So what I end up with is that this supremum, even though I excluded 1 here, still will be 1 to the power n, or just 1. I have not taken the limit yet. But of course, taking the limit for n to infinity of just the number 1 remains 1. So here we have a non-zero limit for the supremum. So we don't have uniform convergence. And in fact, what we will see is that indeed this function g of x does not provide a good approximation to gn of x for finite n. Because look what the function looks like. It has this upward increasing slope. Oh, and in fact, that makes perfect sense, right? If you take x to the power n, you would expect it to slowly start increasing towards 1. Now, the larger n gets, the more the increase happens steeply on the latter part for x. But the limit is really only a straight line and then up. Straight line up. So that looks very different in terms of shape. And yes, we do see when n becomes large that it starts to be going towards that. But it does so in a very strange way, and it's clearly a way where you would not say, well, for n is 5, this provides somehow a reasonable approximation to the function. It clearly does not. Another example. Take a function which is 1 within a certain interval, and let that interval be a function of n. So if x is between 1 over n and 2 over n, then the function is 1, otherwise the function is 0. And x again ranges between 0 and 1 here. Well, how can we then look at the convergence of this function? Well, first of all, realize that actually this interval is always going to be much further to the left. So the upper bound is going to converge to 0. And so what this function is converging to is just a 0 function. Again, let's look at it formally. Take the difference between the function and 0, the limit. Well, there's just of course the function itself here. And then note that for any fixed x between 0 and 1, at some point n becomes large enough such that this upper bound is below x. I mean, even if you take x 0.001, then the upper bound will at some point drop below that when n is large enough. Well, the exception of course is the point 0, but the point 0 is always going to be lower than the lower bound. So the function there will always be 0 as well. So we have pointwise convergence to 0. But again, uniform convergence, as you might guess, does not hold. Because let's do the uniform convergence thing. We look at the difference between hn of x and h of x, which is just this function, this indicator function for this interval. And then we take the supremum over x's between 0 and 1. Well, do that here, and you realize that, well, the value of the function is either 0 or 1. So if we can find an x which is in between these bounds, the supremum will be 1. And in fact, we can always find these x's because there are always x's between 1 over n and 2 over n. So we take an x between 1 over n and 2 over n. The value of the indicator function will be 1. So the supremum is 1. And again, we're taking the limit of n going to infinity of 1, which is just 1 and not 0. So uniform convergence does not hold, and I would again argue the limit function does not provide a good approximation to the finite sample version, because the finite sample version looks something like this, or like this for 5, or 10. The limit function is just a flat line at 0. Well, you can hardly argue that that provides a good approximation. Yes, the bar gets ever more narrow and narrow and narrow, but the bar stays there. So this is some situation where we really don't like the approximation we get here. Now let's take the same example, but then put it more to the extreme. So I'm defining a function h and star, where I let my lower bound and my lower bound is the same, but my upper bound here is going to be larger. So it's only going to decrease to 0 very slowly. So take 1 over ln of n, and I blow up my function with n. Now still we have the same pointwise limit of 0, because for any fixed x, it will always at some point become larger than this upper bound, because this upper bound goes to 0. Ln of n still goes to infinity when n increases. So I have 0 there for any fixed x, times n remains 0. Written out formally here. Then uniform convergence, of course, does not hold. That is, of course, what we have seen in the same way as in the previous example. When you take this supremum, you can always find an x in between lower and upper bound. Well, in this case, situation is even worse, because now we multiply by n. So the supremum now is n, not 1, but n. And the limit of n going to infinity of the number n is, of course, infinity. So here we have a complete difference in terms of the uniform properties. And this difference is even going to increase when n increases. So this is going to be a case, in fact, where if you look at the graph, the asymptotic approximation is extremely bad. And you can here not even say it's getting any better for large n. Yes, the bar gets narrower, but it also gets higher. So n is 500 here. And we're saying that the flat line here is a good approximation to this function here, which has values of 500 up to x being almost 0.2. But still, in terms of pointwise convergence, this is our limit. So this is a situation we could have also in statistics if we focus on pointwise convergence instead of uniform convergence. Now, what we will next need is another characterization of uniform convergence, because this one will actually help us to find out when it is not occurring. And that is the following. So uniform convergence, as we have defined it before, is the same as saying take a sequence, so take x not fixed, but take x a sequence that changes with n, and it should always, of course, take values in the domain. And if the limit of the difference of the functions, so now it's sort of a pointwise limit, but for changing x is 0 for every sequence, then we also have uniform convergence. So let's have a quick look at why these are the same. Well, suppose we start from this being true. So we know that the function is indeed does converge uniformly. Well, in that case, we also know that the difference at the point xn of fn of x and f of x is going to be smaller or equal than the largest difference for any x, right, the supremum. So if this supremum converges to 0, then for sure this pointwise thing with the sequences also converges to 0. And it must do so for any sequence, because this inequality is true for any sequence. Now, to see the opposite implication, it's more subtle, the argument. So suppose that we start out from the point where, indeed, for every sequence x of n, we have a limit of fn minus f at x of n being equal to 0. Now what we want to show is that if we start off from there, then it must be that actually the supremum over all x's of fn minus fx also has a limit which goes to 0. Now the way we're going to argue is by contradiction. Now suppose that actually this would not be true. So suppose that this implication would not hold. Well then, of course, this supremum could be larger than 0. So take that case and say yes, okay, it doesn't hold. The supremum, the limit of the supremum is actually larger than 0. Well, in that case, we're going to find those points x which are actually causing that violation. So we know that this is the case, and there must be some x to which this is actually occurring. And in particular, we can then, instead of looking at the limit, look at any finite n and say, well, there must be some x which gives me a positive number bigger than or equal to c. Because if that would not be the case, well, then this condition would of course not hold, and you would actually have uniform convergence. So we find those x's which are responsible for the failure of uniform convergence. And those x's, well, we actually only need one of them for every n. We're going to put in a sequence x of n. But then, if we look at that sequence, we know its value of this difference is always bigger or equal than c. So we cannot at the same time have that for any sequence, this limit is equal to 0. So there cannot exist a sequence for which this is true. But if there cannot exist a sequence for which that is true, then we also cannot have a case where uniform convergence doesn't hold. So that proves by contradiction that, yes, we can also start from the right-hand side. Now, the nice thing of this definition is that we can use it to check if uniform convergence holds or not in a sometimes simple way. And in particular for us in statistics, this will be a much simpler way to assess uniform convergence. Well, for the first case, remember we did have uniform convergence, and indeed you cannot find any sequence for which this does not hold, because xn will always take values between 0 and 1. Well, this is always bounded by 1 over n, and that will always go to 0. But for the other cases, we could take those sequences. For instance, for x to the power n, what we could take is the sequence 1 minus 1 over n. Take that to the power n, and then we know that that converges actually to e to the power minus 1. Well, that is clearly not 0. So this particular sequence does the job. Well, for the other function, h is actually even easier to find a sequence, because all we need to do is make sure we're in between the lower and the upper bound, so let's go halfway. So instead of between 1 over n and 2 over n, we take 3 divided by 2 over n. And, well, that number is of course always between your lower and upper bound, so it always gives you a function value of 1, and therefore in the limit this will never converge to 0, but instead to 1. So to round this part up, what we have seen is that pointwise convergence can give you very misleading approximations. We've seen in particular this one, which was really extremely bad. Yeah, this is the way we typically do our statistics and econometrics, asymptotics. Now, part of the reason why we do that is that actually many estimators do have automatic uniform convergence. For instance, a very simple case is the least squares estimator. Well, take our linear model, this is our true model, and we can write the least squares estimator, or the difference between the estimator and the true parameter, as this familiar form. Well, we see that actually in this expression there is no beta. It does not depend on beta at all. So you can vary beta whatever you want, but this will not change. Well, that means you automatically get uniform convergence. But if we do model selection first, we don't have that, because there actually our results do depend on beta. And in particular for penalized estimators like the lasso, this is definitely a problem. Now, before we go into the lasso, we're going to analyze the problem in a simple estimator, because that very simple estimator can perfectly illustrate all the problems that you can have if you ignore uniform convergence. And that is what I will do in the next lecture.